Welcome back to the Facilities Design and Logistics course. We are continuing our discussion on discrete location problems. In our previous lecture, we formulated P-center, P-median, and total and partial covering problems, and also the quadratic assignment problem. And in this lecture, we will continue our discussion on quadratic assignment problems, and we will solve an example problem using a heuristic algorithm for the quadratic assignment problem. Let's get started. Okay, so let me first remind you what was this quadratic assignment problem, and we will be discussing this example problem. So in a quadratic assignment problem, the most important property that we need to consider is the facilities that we are going to locate. The new facilities have also interaction between each other, not only with the existing facilities, but between each other as well. In all other previous examples, P-center, P-median, capacitated and incapacitated facility location, the covering, we didn't consider such interactions. And in the quadratic assignment problem, we will consider this case. We will assume there are alternative or candidate sites. These red ones are the candidate sites. And an equal number, there are 4, let's say, candidate sites, and an equal number of new facilities. So in this example, the facilities that we will be locate will be the machines. So there will be 4 candidate locations and 4 machines to be placed in these locations. So if we number these machines as 1, 2, 3, and 4, and the candidate sites also, if we number them as 1, 2, 3, and 4, what do we know? We know the distances between these locations. So between 1 and 2, what is the distance? Actually, it is given in this matrix, in this example. So the distance between 1 and 2 is 5. The distance between 1 and 1 is not given, it is 0. Okay, there is no distance. Of course, we cannot place 2 new machines to the same location. So each machine must be placed on a different location. Okay, so we know the distances, and this distance between 1 and 2 is 5. For example, the distance between 2 and 3. The distance between 2 and 3 is given as 6. But look, something we need to pay attention in this distance matrix. Sometimes this distance matrix is symmetric, meaning that going from 2 to 3 is equal to going from 3 to 2. But sometimes it is not symmetric. For example, in this matrix, if we are moving from 2 to 3, the distance is 6. But if we are moving from 3 to 2, the distance is 5. It means that it is not symmetric, and it can be in real life. Such situations can arise. So while considering the solution or the problem, you need to take this into account. Don't just assume that 2 to 3 is 6, so then 3 to 2 is also 6. Just look at or check the matrix. So the distance between 2 to 3, I can represent it with a directed arrow, is 6, whereas 3 to 2 is 5 according to this distance matrix. So I know all the distances between the candidate sites. But also I know something else. What is that? I know the interaction between the facilities. So when I say interaction between the facilities, actually I'm referring to the number of visits, number of trips that I need to do between these 2 machines. And I am representing, or I'm naming it as the flow between the machines. So if we look at the flow between 2 machines, so in order not to confuse in this example, actually instead of numbering the machines, I used letters, okay, A, B, C, D. So this is machine A, this is B, this is C, and this is D. You can think in this way. It is just labeling, no issues. You can number, you can put a letter, no problem. Okay, so then the flow from A to B is 5. which means that we need to transport material from machine A to B, let's say 5 times. But B to A, we are not moving anything. And it is realistic. It can be in the real life. So this matrix also is not symmetric. Okay? And I know the flow between each pair of machines. I know how many trips between B to C, how many trips between D to B. I know all of them. So this is the problem data. So what we know that there are 4 candidate sites and 4 machines to be located in these candidate sites. We know the distances between the candidate sites, and we know the flow between the machines. Now, in order to understand the problem better, let's do an example and let's try to calculate the associated cost of a given solution. What is that? Okay, in our previous lecture, we said that in our objective function is to minimize the total cost. This is our objective. And we represented the cost with a parameter which included 4 indexes. So it was C, J, K, H, L, something like this. And here J represented the machine. Okay, if machine J is located to candidate site, whereas machine H is located to candidate site L, then this will be the associated cost. And we simply said that this cost is equal to the distance between the candidate sites, DKL, multiplied by the flow between the machines, FJH. And actually, the flow is given in this matrix and the distance is given in this matrix. So we will be multiplying the elements of these matrices. But we need to be careful while multiplying them. Let me show you an example. Let's assume that I decided to locate machine B to this candidate site 1 and machine C to candidate site 2, then machine A to candidate site 3, and machine D to candidate site 4. Now I want to calculate the total cost corresponding to this solution. Okay? So what should I do? How should I do? I am going to start with this one, okay, the cost that is that we will encounter by locating machine B to candidate site 1. Then, okay, I will be calculating the cost of this combination with cost of this combination. So machine B site 1, machine C site 2. So it will be, let me write C. This B, okay, I'm going to write machine B, then candidate site 1, and then machine C, candidate site 2. I will be using this cost, and actually this cost is equal to the distance between site 1 and 2 multiplied by the flow between from B to C. But again, this order is important because this cost is different than this cost. Cost of C located to 2, B located to 1, and it will be D21 multiplied by FCB. Okay, so the first one here calculates the cost if we transport material from B to C. The second one calculates the cost when we are transporting or moving material from C to B. And in our objective function, we need to calculate both of them separately and add them up. Okay, so let me calculate the first of these. What does it say? I need to multiply the distance between 1 and 2, and the distance between 1 and 2 is 5, multiplied by flow from B to C, flow is 2. And the cost, this cost is 10 units, $10. Okay, you can say. What about the other cost? I mean the opposite cost. If we move the items from C to B, it will be C, the cost. C is located to site 2 and B is located to site 1. Again, it will be the distance from D2 to 1 multiplied by flow from C to B. And the distance from 2 to 1 is 4 units multiplied by flow between from C to B, it is 4 units also. And this cost is equal to 16. And in order to calculate the total cost, I need to calculate all these costs and add them up. Okay, so let's do this. Let's try to demonstrate this. Okay, let me just clean up some space here and try to illustrate how we calculate these costs. Okay, for the first one, I am considering, let's say, let's start from this candidate site 1. Okay, B is located to 1, and I am calculating the distance between B and C, I mean the flow between B and C, for which B is assigned to site 1 and C is assigned to 2. So flow between B and C, I'm going to write it here 5 multiplied by the distance between flow between B to C is from the other table, it is 2, and the distance between 1 and 2 is 5, plus B, I am calculating the cost between B and A, where B is assigned to 1 and A is assigned to 3. So flow between B and A, okay, the flow between B and A is 0 multiplied by, actually you don't need to consider it, it is already 0, but the distance is 10, plus then B is assigned to A, and I'm going to calculate the cost between B and D. So B and D, where B is assigned to 1 and D is assigned to 4. The flow between B and D is 3 units, and the distance between 1 and 4 is 4 units. Okay, so this is all the costs associated with machine B, sending items or material to other machines from B. And I need to continue adding up by considering machine C. So I need to consider, okay, the cost of C to B, C to A, and C to D. Okay, C to B. And C is assigned to 2 and B is assigned to 1. The flow from C to B is 3 units, C to B is 4 units, multiplied by distance from 2 to 1 is 4 units, plus C and A, where C is in 2 and A is in 3. Okay, let me clean up. Flow between C and A is 3 multiplied by the distance from 2 to 3 is 6. Okay, plus C to D, where C is in 2 and D is in 4. The flow from C to D is 0 multiplied by distance from 2 to 4 is 7. And this cost is the cost associated with C. Now this is just the solution, and I am trying to calculate the objective function value of this solution, but for that I need to do a lot of calculation. But actually, you know, if you use an Excel sheet, you can do these calculations quite easily. Next thing, I am going to calculate the costs associated with A and B, where A is in 3 and B is in 1. Flow between A and B is 5 units, multiplied by the distance 3 to 1 is 8 units, plus A and C, where A is in 3 and C is in 2. A and C flow is 2, multiplied by 3 to 2, which is 4, plus A and D, where one is in 3 and the other one is 4. So A and D is this one, 0 multiplied by 3 and 4. By the way, this one is wrong. 3 to 2, the distance from 3 to 2 is this one. It should be 5. And the distance from 3 to 4 is this one, which is this. Actually, if you look, what I am doing here, I am multiplying this row of the table with this row of the table to calculate these costs. Okay, 5 times 8, 2 times 5, 0 times 5. And last thing, the last calculation is the costs from D to A, D to B, and D to C. Okay, so DA, where D is in 4 and A is in 3. And let me clean up this. D to A is 0 multiplied by 4 to 3, which is 5, plus D to B, where D is in 4 and B is in 1. So D to B flow is 0 multiplied by 4 to 1, distance is 6, plus D to C, and where D is in 4 and C is in 2. So the flow D to C is 5 multiplied by the distance 4 to 2 is 6. Okay, and then what is our total cost? Our total cost is the summation of all these values. Okay, 2 times 5 plus 0 times 10 plus this plus this plus this. You need to add up all these values to calculate the solution corresponding to this assignment. Okay, actually the problem, if I tell you give me a solution, the solution is very easy. You are just mapping these machines into these sites. You can say, okay, D to 1, C to 3, and etc. Anything is feasible. Any such assignment is feasible. The only condition is each machine should be in a separate location than the others. But then you need to calculate the corresponding cost. Now we are going to solve this example using a heuristic solution. Okay? And this heuristic solution, remember previously we solved the incapacitated facility location with a greedy heuristic. This time we will be using a so-called improvement type heuristic. First we will find an initial solution and we will try to improve that solution. Okay, how can we do it? The initial solution, we call it the construction phase. And actually, any assignment of the machines to the locations will give you a solution. That's it. You can do. This example that I did over here, you can start from that one. Okay? Anything. But we can say that, okay, we are just going to assign A to 1, B to 2, C to 3, and D to 4. Just this initial assignment. Okay, there is no reason to select this assignment. You can select any one of them. But, it can be any assignment, and this is the easiest one that we can do. And actually, this one is the easiest one to calculate its objective function value also. Why is that? Because if you want to calculate the cost associated to this solution, you will simply multiply the flow from A to B by the distance from 1 to 2. Because A is assigned to 1 and T is assigned to 2. So it will be 5 times 5. Plus A to C, in order to calculate the cost, you will multiply this element with this element, which will be 2 times 10. And then the cost from A to D, you will be multiplying this 0 with this 4. 0 times 4. Plus the cost associated with B. In order to calculate it, I need to first calculate this one since it is not symmetric. So B to A, it is 0 multiplied by this distance, 2 to 1. Okay, I am actually multiplying each element in the first tableau with the corresponding element in the second table, in the second matrix. So the second one will be 2 times 6, this, and the other one, this is cost B to C, and the cost B to D will be 3 times 7. And if you continue in this way, the costs associated with C is 3 times 8 plus 4 times 5 plus 0 times 5, and the costs associated with D will be 0 times 6 plus 0 times 6 plus 5 times 5. And if you calculate this one, the total cost will be 147. Okay, this is the cost corresponding to this solution. And this is the so-called construction. What we do, we calculated an initial solution. Right? Now, we will try to improve this solution. Of course, this is just a solution. There's no guarantee that this is optimal. It can be a very poor solution. We want to find a good solution. Our aim with the heuristic is to find a good solution. Okay? So we will improve it. So in the improvement step, what we are going to do is, okay, our current assignment, remember, we said that A is assigned to 1, site 1, B is assigned to 2, C is assigned to 3, and D is assigned to 4. We will use pairwise exchanges. What does pairwise exchange mean? We will simply replace the locations of A and B. Okay? Let me show it in this way. Replace A and B. And what will be the solution? A will be assigned to 2, B will be assigned to 1, C will be assigned to 3, and D will be assigned to 4. But, okay, why we are replacing it? Actually, we are trying it. We haven't decided to replace yet. We are trying it. And we will try and we will calculate the cost of this solution, total cost. And then, this is not the only alternative. Why we are replacing A and B? We can replace A and C, right? And if we replace A and C, then the solution will be something like this. A is located to 3, which is the initial previous location of C. B remains in its current location, which was 2. C is replaced with A, so now it is in 1, and D still remains the same. So we are selecting a pair of machines and replacing their positions and calculating the cost. And compare it with the cost of the initial solution. Remember, this initial solution, we calculated the cost to be 147. Now, if the cost here is less than this initial one, what does it mean? We improved it. But this is one alternative. This is another alternative. But there are many such alternatives. We can replace A with B, A with C, A with D. This is another alternative. Okay, replace A and D. Then, okay, we considered all the alternatives of replacement with A. What we can do, we can consider replacing B with C and B with D. These are also alternatives. So replace B and C, replace B and D. And also, we can consider replacing C and D, the positions of C and D. So these are all the possible alternatives of changing the locations of a pair of machines. So these are all the possible 6 replacement options. But why this number is 6? Why there are 6 alternatives? There are 6 alternatives because we have 4 machines which are allocated to 4 locations. What we are doing actually is, from these 4 machines, we are choosing 2 of them to replace. And in how many different ways we can choose them, we can replace them in these many different ways, which makes 6. It is because of this. If in the problem, instead of 4 machines, if you have, let's say, 40 machines, and if you want to find, if you want to consider all possible replacements of the machines, then it will be selecting 2 out of 40, and you can do this in these many options. Okay, 780 possibilities. Okay, if it is 6, we can do this by hand. But if it is 780, it may be very difficult to do by hand. So what you need to do is you need to have some kind of a computer software. Use this. Even Excel, you can use even Excel for this purpose. But still, for a computer, 780 is a very small number. It can calculate quite quickly, even in seconds, milliseconds. But for us, this will take some time. I mean, for 780, no one wants to calculate it. But again, in order to illustrate this algorithm, this 4 machines is good. We can just calculate 6 possible ways. Okay, let me calculate these. Okay, replacing A and B. If we replace it, what will be the total cost? Again, you need to calculate the total cost like in the previous case, like we calculated. I will not go into these details, but actually, if you want to check, do it as a practice by yourself, and if you want to check it, it should be something like this. 5 times 4 plus 2 times 6, okay, 2 times 10. You need to be careful, and okay, this is the flow bit from A to B multiplied by distance from now 2 to 1, because we replaced the locations of A and B. So now I'm taking the distance from 2 to 1, not 1 to 2. So I am not multiplying each element of the matrices now. So what I am doing when I replace A and B, positions of A and B, I'm multiplying this flow with this distance now, 2 to 1. Okay, so you should be careful while calculating these distances. And then 2 times 6, sorry, just a minute, I did a mistake here. 5 times, no, it was not mistake, I'm looking at wrong place. It is 2 times 6 plus 2 times 10, 3 times 4. I'm not writing the 0 flows here. Okay, they will already be 0. I'm only writing the positive ones, plus 5 times 5. And when you do this calculation, it is 136. Remember, this initial solution, the cost was 147, and the cost of this solution is 136. It is better. So if you compare these two solutions, you will prefer the minimum cost, which is this one. But of course, the other alternatives may even provide better solutions. You don't know it, right? So it's worth trying. Let's try. But the thing is, look, I'm not doing like this. I'm not going step by step. This is our base solution. This is our solution. When I say that replace A and B, I am finding this A to 2, B to 1, C to 3, D to 4. And when I say A to C, again, it is with respect to this base solution, not with respect to this solution. Okay, so when I replace A and C, the solution will be like this: A to 3, B to 2, C to 1, D to 4. Okay, in this one, I am replacing A and C. So be careful with this. And when you replace A and C, you can calculate the total cost to be 150. If you replace A and D, it will be 149. Look, this 150, even worse than our initial solution. It's not good. 149, it is not good. And also, I already have this solution. Among these four, I would prefer still this one. Okay, if you replace B and C, it will be 151. B and D, it will be 142. And if you replace C and D, you will find 132. Which one will you prefer? Of course, the one with the minimum cost, which is this one. So, what will be our solution? It will be A assigned to 1, B assigned to 2, C assigned to 4, and D assigned to 3. Look, the locations of C and D with respect to this one is changed. And we now have a cost of 132. Okay, now what should I do? Should I stop? Actually, no. We just improved this 147. Yes, we improved it. It's very good. But the thing is, maybe if I try to change the locations on this solution, locations of the machines on this solution, I can even improve the objective function value. So why should I stop? Let's continue. Let me write this solution here. Now we have A to 1, B to 2, C to 4, and D to 3 with a cost of 132. Now I can again consider changing the two machines. If I replace A and B, what will be the solution that I will get? A is assigned to 2, B is assigned to 1, C is assigned to 4, D is assigned to 3. Look, this solution is totally different than this solution, and it is different than in any one of these previous solutions. In these previous, I tried 6 possible alternatives, and none of these 6 alternatives included this version. It's a different one now, and and by this change, I am calculating, or I am trying a different alternative. And if you do this change, you would obtain the cost to be 139. Again, you can replace A and C in this. Now this is our base, and I am implementing these changes to this base solution. And if you do this, you will obtain 140. If you replace A and D, you will find 120. B and C, you will obtain 122. B and D, it will be 156. And C and D, you will obtain 147. And actually, look, this one, if you implement this solution to this one, you are returning back to the previous. So actually, you don't need to consider this one, because we already evaluated this in the previous case, and we came to this base solution, this solution, from that one. There's no need to evaluate that anymore. And if you look at the alternatives, we can see that the best is replacing A and D, and the total cost will be 120. So what will be the solution if we replace A and D? So A will move to the position of D. Look, D was in 3, so now A will be in 3. B is still in 2, C is still in 4, and D goes to the location of 1, of A. Okay. Now this is our base solution with a cost of 120. Okay, we started from 147, we improved it to 132, and now we improved it to 120. But how do we know that this is the best solution? We can continue to replace it, we can continue to change it. So what are the possible changes? Again, in this solution, you can replace A and B, then A and C. If you replace A and D, it will return back to this solution, the previous solution. So there is no need to evaluate that solution. Okay, I mean the previous solution is this one. If you replace A and D, you will obtain this one. So there is no need to consider this anymore. Then B and C, and B and D, and then C and D. 6 possible cases again. And you need to calculate their objective function values. Okay. And if you do that, actually, I don't have the values here, but the thing is, none of these less than 120. So we already have a solution with a total cost of 120, and if we try to replace the machines, we cannot improve it further, so we stop it. The solution that we obtain is this: assign A to site 3, B to 2, C to 4, and D to 1. Now, how many alternatives we tried starting from the beginning? Look, we initially started with this solution, and then we tried 6 possible replacements. So 6 alternatives, 1 the original plus 6 alternatives here. Then at this stage we replaced 6 alternatives, but one of them was the same with the previous one. Actually, we tried 5 different alternatives. So we started with 1 and then tried 6 alternatives, and in this stage we tried 5 possible alternatives, and at this stage we additionally tried 5 alternatives and then stopped. So in total we tried 17 possible replacement options, 17 possibilities, okay, to find this solution. But actually, how many solutions are there for this problem? So in order, how many different solutions do we have for this problem? Actually, you can think about like this. There are 4 locations, and we are going to select, or we are going to assign these 4 machines to these 4 locations. So for the first one, how many different machines can I locate? 4 different machines. If I locate one of these machines to here, how many possibilities do remaining alternatives do I have? 3. And I am selecting one of them and locating to there, and then remaining one is 2, and then remaining one is 1. So actually this is the total number, which is 4 factorial, which makes 24. Now compare this. If you want to find the optimal solution, you need to try 24 different possibilities. But in this heuristic, I tried 17 of them. And you can say, why? Just try 7 more others that we haven't tried and got the optimal solution. Why don't you try it? And I will come with this argument. Okay, now if instead of 4 machines we have 100 machines, how many possibilities do we have in total? It will be 100 factorial, right? In order to obtain the optimal solution, you need to try 100 factorial different alternatives. Can you calculate this number? What this number is? It's huge. Even for a computer, it's huge. Instead of trying these 100 factorial cases, if we use this heuristic, how many alternatives we will try? Initially, we will start with a solution, 1. Then at the first case, we will select 2 of these 100. Okay, it will be 99 times 50. Let me calculate that number. 4,950 alternatives. This is the heuristic. Okay, if you try in the first step, you will get 4,950. Then in the second, again you will try same number of alternatives, but one missing. One will be the previous. So it will be 4,949. And in the next, 4,949. And it will be increasing by this. So assume that you stopped after step 10. You continued replacing these machines pairwise in 10 steps. So what will be the total number of alternatives you try? 4,949 multiplied by 9, okay, plus 4,951, and it will be 49,492. Okay, with the heuristic you are trying these many alternatives. If you want to exact optimum solution, you need to try this much. So can you compare these two numbers? You cannot. This is huge. You cannot compare them. Okay? This number, it is also big, but it is big. It's a large number for us to do it on paper, but for a computer, this one is very easy. Again, in seconds, you will get the solution. But for this one, even with the computer, you will not be able to get the solution in hours, maybe days. Okay, so therefore, for such questions, heuristic algorithms provides us good results in reasonable time. And the thing is, don't just compare or judge the performance of the heuristic for small problems, but we use heuristics usually for larger problems. Okay, so this example illustrates such a heuristic algorithm.